All right, so covering Rust Rustaceans, Chapter 2. So who am I? I'm Matt Davis. I program video games. That's my background. Originally, I spent all my day writing C++, but now I try to spend as much time as I can writing Rust. And I also help organize the Rust and C++ Dragons meetup with Kiera and a couple other people. So what are we talking about today? We're going to talk about how types affect memory use. We're going to talk about size trait and what white pointers are. We're going to talk about static and dynamic dispatch with those traits. We're going to talk about generic trait parameters versus associated types, and orphan rule, trait bounds, market traits and types, and existential types. There's a lot of stuff to cover in just a few pages in this book. So let's talk about alignment. The chapter starts with straight into alignment. And alignment covers about how the CPU interacts with RAM. So when memory is aligned, when a value is aligned in memory, that means that the CPU can fetch a single value using a single read. Now, it's a little bit more complicated than that in modern architectures because modern CPUs read cache lines and stuff like that. But you can think about it as a CPU reading on a 64-bit process, 64 bits at a time. And a misaligned value is something that is aligned over a couple of those 64-bit words. So if you can see the diagrams here, if you on the first row, you can see that a nicely aligned 64-bit value, you read those one set of eight bytes and you grab the whole 64-bit value. But when you're misaligned, the CPU has to do a little bit more work. It has to read a couple of those 8-byte values and then do some shifting and masking and stitching together values to finally get that value into your registers. Now, this is done by the CPU transparently to the programmer, but it does take a bit longer to do than if the value was aligned. So you want your values aligned. And the Rust compiler and many other compilers do this for you behind the scenes. So generally, you want values to be aligned kind of based on their sizes. So 8-bit values can be aligned anywhere. They're just bytes. You can put them anywhere in memory. The CPU can just read them quite fine. 16 bits, you want them on the sort of first, third, fifth, and seventh bytes in a group of 8 bytes, and so on. So this leads us on to how we lay out values when we start using structs. And so Jon Gjengset book covers this. It starts with how C is done. Now, C isn't smart with structures. It does exactly what you ask it to do, and so you can emulate a C structure by adding the hash repr C at just before your structure. And what C will do? C will do the alignment, but that's all it will do. So this leads to a lot of wasted space. So if you imagine this foo structure when you have tiny, normal, small, long, short fields. Now it puts a tiny in first. It can put as a byte size, a bool, and it can just put in the first byte there, no problem. So you're already aligned. But then it moves on to the 32-bit value, and it can't just put it on the second byte because now that 32-bit value is misaligned. So it pads it with 3 extra bytes and moves it across. So the 32-bit value is now aligned on a 32-bit boundary. The next value is an 8-bit, and then we had a 64-bit, and this is the worst case because now we have to pad with 7 bytes, and so on. But we haven't just got padding between fields. When you create the structure, the entire structure needs to be aligned as well. That means that its size needs to be aligned according to the highest sort of largest field within that structure. Because we have a 64-bit structure field in that structure, that means we then have to pad up to the alignment of 64 bits for the final structure. The reason C does this is because if you have an array of values, the second value will be aligned and the third value will be aligned and so forth. So we have to add another 6 bytes at the end. So our total size of that structure is 32 bytes, even though we only use about half of the memory. There's a huge amount of wastage. This is really worst case. Now, Rust does things a little bit differently. Rust has the freedom to reorder your fields in memory to remove all this padding. And you can do a Rust structure by adding repr Rust, which is totally redundant because you can just remove that and not have any repr declaration there, and it'll be your normal Rust structure. Of course it will. But what it will do is it will reorder the fields usually with the largest fields first. This minimizes the actual wastage of bytes to alignment. So we'll put the 64-bit first, then the 32-bit first, then the 16-bit, and then the 28-bit. And the size of the structure follows the same rules as C. It will align the size according to the largest field, which is 64 bits. So we end up with only 16 bytes, literally half the memory that a C structure would use in that case. Now, this has been pulled out in Jon's book just to highlight the worst case. But you can imagine if you have hundreds of structs in your program, huge arrays of values of these structs, you can imagine the wasted memory you have and the increasing cache misses and all kinds of performance issues with your software. And the layouting of the types is pretty much as you expect. With tuples, they pretty much represent like a struct. So where you have a type, like a tuple of 3 types, that's like a struct of 3 types. It's aligned in exactly the same way. Arrays, they're just contiguous sequences of values with no padding in between. A union, unions are not used so much in Rust because we use enums for a very similar thing. But a union in Rust is exactly like a union in C and C++. Values are overlaid on each other, and essentially each variant of that union, the layout is independent of each other, and the alignment is essentially how we choose to have the final size of that union. Whether it is aligned on 64-bit or 30-bit, it's based on the maximum field size across all the types in the union. The enums is exactly the same. It's pretty much a union with an extra field, and that field is determined. The size of that field is determined by how many variants. So if you have a variant of, say, if you have like 30 variants in your enum, a single byte can hold 0 to 29. And so it will put the a single field of a byte, and so there will be some padding in an enum. However, in Rust, and this wasn't mentioned in Jon's book, but in Rust, some types can optimize that extra field away. Whenever you do an enum with non-zero values, like option. Or for option on a pointer, the compiler will optimize that and essentially do 0 for none and the pointer for the sum part of the option. So you can get away with the extra field and no padding. So this leads on to the size trait. Now, this is a trait that's ubiquitous in Rust, and it's literally everywhere, but you do not see it because it basically means that if a type has this trait, it means that its size is known at compile time, and most types implement size automatically. You don't really have to think about it. Pretty much any primitive, most primitives do size, structures, and so forth. But there are 2 common types that do not. The first type is trait objects, which we'll cover a bit later. An example of this is using the din keyword. And the other one is slices. Now, what these 2 types got in common is that we do not know the size of the value represented by that type. The first trait object, it says a object that implements this trait. We don't know what the object is. We just know that it implements this trait. So we don't know its size. Again, with a slice, we don't know the size of a slice. And so, we know it. We have a pointer to memory that contains these values, but we don't know the size. So they do not have the size trait. But there's a rule in Rust that all struct fields, tuple types, function arguments, return values, variable types, and array types must all be sized, because the compiler needs to know how big they are to actually generate the code to access them and manipulate those values. There's a trait called question mark size, and that question mark pretty much means maybe. So all trait bounds are implicitly sized. So whenever you deal with a trait bound, which is essentially, can you see my cursor on the screen there at all? So this bit here, that's a trait bound. We're saying that type T must have these traits. And all trait bounds are implicitly sized, which means you don't have to do code on sized on it, right? However, if you don't want to size, then you can use the question mark size and say, okay, we're opting out of size. Size doesn't have to be sized, so we can accept dynamically sized types such as slices and trait objects, and we allow them to be used. So this function does that, and all it does is prints out a value that can accept a maybe size, maybe not. But if you notice, the actual argument in the function is a reference to that type. So a reference to a non-size type is a size type. So we can have it as an argument in the function. And this allows us to do print hello world. Now, if we didn't have this part, this line will come up with an error. You can try it yourself. This is because this string is an str type, which is another dynamically sized object. It's pretty much a slice of U8s that are guaranteed to be characters, UTF-8 characters. Usually you have to do a %str if you need to pass this in, and Rust. And if you do that, Rust will convert this str into %str for you through automatic implicit casting. But here we say, okay, we add this, and now we can accept this argument. Next subject is wide pointers. Now, wide pointer is something that's, I think, Rust wide pointers is something that is uncommon in languages. C and C++ do not have wide pointers. And essentially what a wide pointer is a normal pointer, but it has extra information, another word attached to it to give, which give extra information to complete the type. And what that information is depends on the type. Usually in C++, the pointer itself will point to that extra information. So the compiler automatically generates this wide pointer whenever you reference a dynamically sized type. By referencing, I mean you put an ampersand in front of it and you ask for the address of it. So if you put a reference in front of a slice, that extra information that you see that's part of the wide pointer will be the length of the slice, and that's all built into the compiler. You don't have to care about that. And similar thing for trait objects, which we cover a little bit later. But crucially, it's important to know that wide pointers are sized, right? The compiler knows how big wide pointers are, so you can pass them in as arguments to a function. You can do return values and all those other kind of things, right? The compiler will by having that reference, you convert a non-sized type into a size type. Monomorphization. Monomorphization is the process of going from a generic type to a non-generic type. Mono meaning one and morph meaning change. And this happens to all generic types and generic functions when you use them in the code. So the compiler will make a copy of the type or function, whatever is generic, substitute that type in that you want, and it will generate a brand new function for that. This has costs, of course. The program is is larger, and the compilation takes longer. But there are tricks to reduce bloat. So if you have a generic function, and part of it doesn't have to be generic, you can have an in function inside, which is non-generic, which your generic function can reference internally. And the non-generic internal function will not be monomorphized at all. Why is this important? Well, this is important to talk when we talk about static versus dynamic dispatch. Now, static dispatch is one of the other two ways of calling methods when you have a reference to a trait. So if you look at the code above, we can see that we extending string. We had a new function called contains, and it takes an impl pattern right here. Now, when you ever see an impl pattern as an argument to a function, it really is sort of syntax sugar for generic function. So when you see this line, you're really reading this line. You're creating a generic type T, which is restricted to the trait pattern, and you're passing that in as an argument there. This just makes it read nicer. So the compiler, because the compiler knows the type at compile time, it will know where the method for that type is at compile time, and so it knows the compile time address of is contained in. And so when it generates the contains function, when you use it, it knows all the types. So unfortunately, there's no one address for any type, right? Each type will have their own version of methods because they use different types internally. So the compiler has to generate a new function. So for every given copy of a method, the address we are dispatching to is known statically, and that's by known statically means known at compile time. This is where the static dispatch gets its name. So when you call is contained in here, you're statically dispatching to the is contained in method, and it can just call it directly like a normal function. The alternative is dynamic dispatch. So dynamic dispatch uses this syntax, the din keyword before a trait. Now, this is used by the dynamic dispatch is used by trait objects. Now, a trait object is some object that you only have a trait interface to. So anything with din in front, that's a trait object. This is saying, okay, this object, whatever it may be, implements the trait pattern. And of course, we have to have a reference to it because, again, we need this argument to be sized. And a trait object is a combination of a trait. A combination of a trait and a virtual table now, or a V table. V table just contains a list of all the addresses for all the methods that have been defined for a particular type in an impl block. It's analogous to C++ V tables. When you create a class in C++, every C++ class has a V table part of this type. Now, when you create a reference to a trait object, that P is a wide pointer that contains both the reference to the struct, the pointer that you'll manipulate, and a reference to the V table as well. This second extra bit of information will help Rust call the correct method at runtime. Now, the address of that method is determined at runtime, hence dynamic. And this technique can cut compile times. The program size is smaller because we're not monomorphizing functions, and there's more efficiency with the CPU cache and so forth. However, because we have this indirection, and because we don't know, the calling code doesn't know what type it's dealing with ultimately at runtime. At compile time, the compiler cannot optimize as well. And there's a small call overhead as well with when you call in functions indirectly through dynamic dispatch. Dynamic dispatch is exactly the same mechanism as you would call virtual methods in C++. So let's talk about trait objects. I've gone over a little bit what trait objects are. They are some sort of value, some sort of struct which implement a trait. But not all traits can produce trait objects. So any method that returns a self in the signature, as a self as a type of return value within a method in a trait, that automatically disallows that trait to become a trait object. Because if you did have a self, then you don't know at compile time exactly what type of object you're calling during dynamic dispatch. So what does that function return? We can't generate the code for that because that's only known at runtime. Likewise, generic methods can't be used. So if you have a generic method in a trait, that means you can have multiple of those methods depending on how many types you pass into that generic method, right? Which means that your V table is now dynamic. You don't know at compile time, how big that V table is. And so that disallows that trait from becoming a trait object. You can't put the din keyword in front of it. And also any method without a self parameter can't be a trait object either, because when we do want to call that object through a y pointer, that which method do we call, right? We don't know what to dispatch to. So static versus dynamic, which do you use? Well, as a general rule of thumb, you kind of want to use static for libraries since you don't know the user's needs. They can still use dynamic outside if they want to, but the reverse is not true. If you have dynamic in libraries, your users force use the dynamic dispatch. And you can use dynamic. You should try to use dynamic only in your own binaries, your own applications, because it doesn't matter. You make those decisions. Dynamic dispatch looks cleaner. You got the less noise with generic parameters and so forth. It compiles faster, but it runs slower. Static optimizes better, but increases programmer size. So, choose your poison. So we got a word on generic traits. So there's two types of ways of doing generic parameters in traits. There's the actual use of generic parameters. So you use a typical generic syntax. You have the T in angle brackets there. But traits also offer an associated type, which you pass using the type keyword within the trait. And when should you use associated type over a generic parameter when you're designing your generic trait? Well, there's a simple rule of thumb, which Jon goes over in his book. He says you use an associated type if you expect only one implementation of the trait for a given type. So basically, try to use associated types whenever you can. It's just much cleaner and nicer, because with generic parameters, every time you use that trait, you have to carry those parameters with you at the call sites everywhere. Whereas associated types, they only need to be defined once inside an impl block, and then you use that everywhere. Then Jon covers straight after that the coherence property. Now, the coherence property means that for any given type and method, there's only ever one correct choice for which implementation of the method for use for that type. That means that when the compiler is generating code, it knows exactly what you're talking about. So it's imagine writing your own display for bool. There's already a display implementation for bool in the standard library. So you write your own one. Which one is going to be used? There's a conflict, right? Whenever you do your din display and you pass in a bool, a reference to a bool, which method are we going to use? So this breaks the coherence property. So to combat that, there's something in Rust called the orphan rule. And so we can have restrictive solutions to this problem. We can say that only the crate that writes a trait can use it in its own implementations. Now, this basically makes traits useless, right? This means that we can't implement the trait outside, say, of the standard library. The other extreme is that you can only implement traits for your own types. Well, that basically means you can't share your trait now, right? So we want a better solution than this, and we want downstream crates. These are crates that use the traits to implement upstream traits for their own types. But we also want to have upstream crates to be able to add implementations of their own without breaking downstream code. So the orphan rule is this. It's in bold on this slide. You can implement a trait for a type only if the trait or the type is local to your crate. If both of them are not local to your crate, you cannot implement you can implement that trait for that type. I can go ahead and implement display for bool because neither display or bool are local to my crate. This is the orphan rule. However, it's never that simple. So there are some exceptions to the orphan rule. And this is something I learned by reading Jon's book. If you read the normal Rust book, you hear about the orphan rule, but this I didn't hear about. So blanket implementations. This is when you say, okay, I want to implement this trait for a bunch of types. You quite often see these in like convenience conversions and stuff like that. But the rule is only crates that define the trait can do blanket implementations. This means that if I wanted to implement display for all references, so reference T, for example, then I can only write that code in the crate that defines the display trait. There are some fundamental types. That's reference mute, and box, and they're marked with hash fundamental in the standard library. These ignore the orphan rule. So if you implement debug for reference to my type, that will work. You could probably implement debug for ampersand bool as well. And then there's this thing called covered implementations. And this is actually quite difficult to get your head around. I personally never run into this when I've been writing code, but I guess it's good to know. But there's some exceptions to the orphan rule, and this is when you're doing things like from my type for vector. Now, both from and vect are foreign types. They're not going to be local to my crate because they're in the standard library. However, my type is in my local crate. So the Rust allows you to be able to define from my type for the vector I32 in your local crate. And this is really complicated set of rules. So if you implement with parameters 1 to parameters n, you pass your foreign trait with generic templates T1 to Tn, and for T0, it's allowed if at least one Ti is a local type. So one of these is local to your crate. So for example, my type is local, and no T before the first Ti is one of the generic types P1 to Pn. And unless that T is a cover type, and a cover type is anything that appears as a type parameter to another type, e.g. the T in a vec T. So this is really complicated, right? And the Rust compiler will handle it and give you error messages if you sort of violate this. I've personally never run into this at all, so I wouldn't worry too much about it. But the book does give you some valid and invalid examples. And so that rule, you can do all these types here. and these ones are invalid. And you can probably go through them step by step and go through those rules and try and figure out exactly why they're invalid or why they're valid. But I didn't want to do that. I'm going to take Jon's word for it. It is a little complicated. Trait bounds. So a trait bound is for any given type T, it requires the following traits to be implemented for it. They're given as generic parameters. So you could write a function foo, and this type with a colon and a list of traits. That is what's called a trait bound. Or we can use it as a where clause, where we take it out of the angle brackets and put it down as a separate where statement here. Sometimes, if you got some complicated ones, I generally prefer the where, because it pulls it out to the signature and it makes it a little easier to read. Now, they don't always have to be of the form, okay, here's my type T, and it has this trait. And Jon does this example in the book, and it's quite difficult to understand what he's talking about. It's the first time I read something in this book where it needs to do a little bit more work on explaining what he's talking about. I had to go online to a discussion site about this particular chapter, and other people have brought this up. But essentially, if you wanted to create this particular function, I made this function up, but I tried to come up with a function that demonstrated what Jon was talking about in the book. So if you've got a function, just create a hash map, right? And we pass in a data vec usize, and we're returning this type. You might say, okay, I have to now look into the hash map and I have to figure out what the traits are, the trait requirements for the hash map parameters. So the first one is the keys type, the second one is the values type, and the third one is the hashing type, right? And I will might look in the code and say, okay, T needs to be hash and EQ. So T needs to implement those traits, and S needs to implement those traits. And I could do it this way. But Jon's saying, okay, you can just do this, right? Rather than talking about exactly what T and S is, talking about those types, it's talking about the type that we really care about, and the type we really care about is the whole hash map type itself. And we're saying, okay, the hash map has to implement from iterator. And the reason why we need to do that, and this is what wasn't explained in the book, is that Jon was assuming that this create hash map only needs to use the collect method to construct the hash map. So we're taking the vector, we change into an iterator, and we're calling collect. And so therefore we only care about that the hash map can collect, and so the hash map needs to implement the from iterator. So his message was that you can talk about your the bindings at a higher level, and not necessarily, you don't have to talk about individual parameters. You're not talking about T and S. You're talking about the whole hash map. And at times you can read better. As I said, Jon's example in this, I don't think was that great, and he didn't explain it fully. Right, so ambiguities with associated types. So it briefly talks about referring to associated types inside trait bounds. And you can refer directly to associated type by putting the outer type, what's implementing your trait, and the name of the associated type. However, if you have a trait that implements multiple, if you have a type, that implements multiple traits, so you have a struct that has multiple interfaces to it, and two of those traits actually have the same associated type with the same name, then you can be more specific about which trait you're talking about. And you can do that with the angle brackets, outer type as the trait, and then colon associated type. This is a bit long-handed, right? but in practice, I really come along and see this. Then he talks about higher rank trait bounds. This is scary stuff. This is when you want to fully decorate a binding in that where clause that says, okay, this in reference implements this trait for any lifetime. And it comes with the syntax with the for. And it's saying, okay, for any lifetime, we're going to call A, a reference to type T with the lifetime of A must follow this trait. And usually you see this a lot when you're dealing with function traits, the fn, the fn once, and the fn mute, because you want to be able to put lifetimes, collect, say, maybe parameters or return values to each other with a common lifetime. And so, for example, here's a function that takes a parameter reference to a type T, but returns maybe something inside T and returns a reference to U. So because of that, they need to have the same lifetime because U needs to live as long as T. And we encode that in Rust as part of the actual type. But to have that lifetime just introduced, we want that lifetime just introduced in the binding. We don't want to put that lifetime in the signature of the function. We can use the for right here and say, okay, I want this a function of this signature, but with a lifetime. But and here's a lifetime. I'm just going to introduce it here just for the purposes of this binding. But luckily, Rust can usually figure this out. The compiler can figure this out without you, so you don't even need the for pass. So you can just do this, right? But the for is explained in this book when you see it. Jon says that when he wrote the book, it only appeared 3 times in the entire standard library. So it's not something that's common that you probably come across. But if you do, you know what it means. It basically means, okay, I want to declare a lifetime that's only valid, that's only useful for this particular trait binding that I'm doing right now. And it has a silly name, higher rank trait bounds. It's a stupid name. It doesn't conjure any imagery about what it actually means. So it moved on to marker traits. Marker traits are traits that have no methods or associated types. They allow you to capture binding semantics that are not available in the code. And standard library defines a few of them. You might be familiar with them: send, sync, copy, size, we talked about earlier, and unpin. But most of these marker traits in the standard library are what's called auto traits. The compiler will automatically implement them for any type whose all their subtypes also implements that marker trait. So if you have a struct that all the fields in it implement send, then the struct is also automatically send. There's a set of exceptions. Copy is not. So even if a struct has all fields that are copy, it will not automatically implement it because maybe the user doesn't want to copy that structure, right? Maybe the user wants to restrict copying of that structure. Marker types are similar. These are types with literally no values. So these are unit types. They can mark types as being in a particular state, and they're useful for stopping users misuse an API. So, for example, they normally use as generic parameters. So, for example, we have these marker types authenticated and unauthenticated, and if we want to create an SSH connection, and so we can have a parameter that's just associated, a generic parameter that's just associated with the struct that doesn't do anything, doesn't change anything, but it gives it a different type. So if you open a port with a password, you get an authenticated back. If you open an unsecure port, you get it unauthenticated. when you implement SSH connection, you have to use something called phantom data, because you can't have in Rust a generic type that isn't used within the struct. It will come up with an error saying you're using a generic parameter that you're not using. Yeah, you can't do that. So there's a thing called phantom data that you have, which takes no memory, and you can put inside your struct, and it consumes that generic parameter to stop that Rust error. And that's covered in the next chapter. So we're on the last bit here, the last part of the chapter. We talked about type inference and existential types. So I don't know if you ever noticed, but if you try to do define anything at a global scope in Rust, you have to always declare the type. Whereas inside a function, if you use let, you don't necessarily have to declare the type, because Rust mostly can infer it for you. And then there's a few reasons about this, but Johnny goes into one of them. He says the primary reason is when you're reading the code, inference is easier when you have known points to start from. That you can go to the global scope and see the types that are used elsewhere in all the functions and so forth. But not all types can have a name. And this is similar in C and C as well with lambdas. So Rust can use has to use an impl-trait syntax to reference generated types that the compiler might create, such as closures and async blocks. And we just leave it up to the compiler to figure out. Now, this is normally in like a return value or within a binding. But remember, impl-trait in an argument position is not an existential type. That is just syntax sugar for doing a generic parameter. And that's it. That's the end of that chapter. And do we have any questions or answers? Well, hopefully I've got the answers, but do we have any questions?
Awesome job, Matt. That was brilliant. People can either like put questions in the chat or unmute yourselves. Whatever, that'll work.
It was awesome, Matt. Something interesting I found, like when I was reading or trying to read on the white pointers and the dynamic dispatch. Again, Jon has a video, probably from 2 years ago, maybe older, I don't know. And it was really good also to watch. And it wasn't that lengthy, if I remember correctly. That was some time ago.
That's another link that needs to be shared in our new hash video channel on Discord that we haven't set up yet.
Might be one of his like he's done some that are, I think his Crust of Rust ones, they can be quite long as well, but I think some of them can be quite short, where he's focused on a specific topic rather than just doing a live stream.
Oh, they're great, all of them. Even the long ones, right? You just have to put some time aside, but you will come out a smarter person whenever you watch them, or you come out completely confused. One of the two.
I lied. It's 2 hours and something.
That's short for one of his videos.
That sounds more right. His Crust of Rust ones are usually like, 1.5 to 3 hours, I would say. I think he tries to cap them at 3 hours. That's a guess, but.
So someone's asked me a question. It's off topic. Do I use Rust for game dev as well? Not professionally. Professionally, there's a couple of companies that use Rust for game dev that I know of. We still all use C++, unfortunately. But I do use it for game development personally in my spare time. I'm working on a bunch of things. I switch between some of my own code and Bevy, which I really like Bevy. I really like the foundation of Bevy. I've already given a talk on its ECS previously. And I think it's the best ECS system there is out there in terms of ergonomics and speed and just the whole package. What's sitting on top of that foundation, I'm not so sure about yet. for me personally, the jury's still out on Bevy, but it's just immature, right? Which is fine. It hasn't reached version 1. Any other questions? So I've either completely befuddled everyone because I went through that breakneck speed, or I explained it incredibly well and everyone knows everything about types in Rust now. So one of the two extremes, I think. No questions. Claudio, if you go to our YouTube channel, you'll find it there.